It's about buffer overflow. We will introduce one of the buffer overflow. It's called stack overflow, because stack overflow is easier to introduce, and it's also one of the main buffer overflow attack in the real internet. Again, I used many slides from other faculties and some online presentations. Okay, so what is the buffer overflow problem? We will use C code as the example, but it's not just exist in C language, but also exists in some other programming language. But most commercial software, they were programmed in C. Of course, right now there are many there are many software they programmed in Python and Java, but those are more like a front-end software. The back-end software, which require high-speed, more efficient use of the computer resource, they still rely a lot on C code, because C is the most efficient program language to use the hardware resource. And in addition, many software companies, they have more than 10 year or 20 years software base. All those previous program software, they were programmed in C, and they were mature software modules that generated by the software company for many years. So this software module will be reused a lot of time. Most of them are generated in C as well. Okay, so what's the problem here? The problem here is that this local variable buff, it was allocated with a certain memory size, like 10 bytes memory for this local variable. But this string copy function will copy a user input string. This string is a user input string, but string copy function doesn't verify whether the user input string is over that predefined size or not. So if the user is malicious, then the user could input a very long string here. Then the string copy will copy that very long string to this very small limited size of the variable. Then this copying action will overwrite all the neighboring memory of this variable. Then those overwritten could overwrite some important system variable, and that will cause most likely it will cause the program to crash, because you overwrite many important data on the memory. You cause the system to be totally wrong, then you will crash the system. But if attacker put this overwritten data in such a careful way, it overrides some system value in a specific way, then they can compromise the system. They can gain access to your system. So if this function is called using this long string, this will cause the program to overwrite in some neighboring memory. Most likely it will cause the program to crash. So that's a problem. The problem is that user input string is too long than the predefined memory allocation. The general idea is to give servers very large strings that will overflow a buffer in the software code of the server. For a server with a sloppy code, it's easy to crash a server by overflow a buffer. So this is a very, as long as you know there's a security bugs, you can crash that server program very easily by giving this large input. So this will cause a denial of service attack to a server, because you crash that server, then the server will not be able to serve any other legitimate user anymore. But a crafty attacker, they can input this long string such that way that they can actually gain access to the remote server. Then they can do whatever attacker want on the remote server instead of crashing. So this is a buffer overflow attack. And we use C as the example to introduce. So you should have a little bit knowledge about C and also knowledge about the stack in operating system, how the stack works. Okay. So what is buffer overflow attack? The intention is that the basic intention is called denial of service attack, because you can crash a server software very easily with a single input to the system. Relatively easy to do as long as you find an overflow hole, then you can crash the software very easily. Another more advanced intention is the arbitrary code execution. Most likely you can generate a remote shell on that server. Then once you generate a remote shell, you can run the command on that server in whatever way you want. Most likely those remote shell will have root privilege, such that you can do whatever way you want on the compromised system. Because most server program, they're running with the root privilege. So once you compromise that server program, your generated shell also has the root privilege. The code injection steps is that you inject the attacking code into the buffer, into that local variable. Then you overflow the return address for that function. Basically, we are doing stack overflow. So overflow the return address on the stack. Once you overflow return address, you put a carefully craft a new address in this place. You will redirect the CPU's flow to your own code, your own supplied code. Then your own supplied code will be executed. Then most likely it will generate a remote shell for the end user. But you can have some other attack code in that. So execute the attack code. So the target, buffer overflow target could be stack, could be heap, or static area. So heap overflow is the overflow of a dynamic allocated memory, because dynamic allocated memory, they were allocated in the heap section. Static allocated variable is in the stack memory section. You could also modify some parameters. So instead of changing the return address, you can try to overwrite, because when you overflow a buffer local variable, you overflow the neighboring memory. If you know that the neighboring memory is used by another variable, then you can change that variable's value. So you can modify that variable's value such that you change the program. But suppose that variable is a privilege flag. Like if the variable is 0, then user does not have privilege. If the variable is 1, user has the privilege. Then this parameter modification can change that variable from 0 to 1 to give the user certain privilege. So that is a privilege elevation. Change privilege to some control variable. So this attack is called non-pointer non-control flow attack. You are not changing this program flow return variables. Injected code versus existing code. The most simple buffer overflow attack is that you inject your code into the overwritten variable, local variable. Most likely you just inject a shellcode, because shellcode is very small. Shellcode is only 20 to 50 bytes. So it's very easy for you to inject a shellcode. But you can also use existing code. So you don't inject any code by yourself, but instead you just run some existing program by the operating system. Like you can change the control flow. Instead of return back to the program, you change the control flow to run like a delete function provided by the operating system. Then you can delete many important data on the target server. So inject code or versus existing code. Absolute or relative address dependence. For example, if you want to use some existing code provided by the operating system, you need to know where those existing code like make dir or delete function or copy function exist in the operating system in the memory. So you need to know that their address. You can use absolute address or relative address depend on how the program is running. And related attack to the buffer overflow attack is integer overflow and format string attack. I will introduce both of them. In most vulnerability of buffer overflow attack is because there is the integer overflow bugs. The attacker utilizes integer overflow bugs, and they can generate this buffer overflow bugs. So that's the related attacks. So stack overflow. We will introduce stack overflow, not heap overflow, because heap overflow is much more complicated. Stack overflow is relatively easy to do. So the majority of buffer overflow attack, they are doing stack overflow. So what is a stack? Stack is that when operating system load a program to run, the code will start from somewhere in the memory. Then the static data, like when you define some global variable, those global variables will be put here. There are some memory place used for dynamic memory allocation. The shared library would be the shared library by the operating system. Like operating system provide a lot of function that any program can load and run. So that's a shared library. Then there is a memory space used as a stack. And the kernel space is operating system code. They exist in that kernel space. So this stack is going from lower address, grow from lower address to from higher address to lower address. So that's the so C calling stack. When a function call is made, the return address will put in the stack. Then this is hard to say. So let me give one example. Like suppose this is your program. In your program, you have a function call. So for any program, you will have some function call. Then when this function is called, so suppose this is this function code. When this function is called, the function's input parameter will be first pushed into the stack. Because remember, the stack is growing from the higher address to lower address. So whenever a function is called, the input variable will be pushed to the stack. Then it will be the return address. Return address will be pushed to the stack. So what does the mean of the return address? Return address is basically means that when this function call is finished, where should the CPU continue to run the next instruction? So from this code, we know that after this full function is finished, the next instruction should be y = 3. So the return address is basically the address of this instruction. So the address of this instruction will be put here. So that is called return address. Then some other like a saved base frame pointer, we will mention that later. Then it will be the local variable defined in this function. So all the local variable defined by a function, they will be created in the stack. So that is how the stack is used. After this full function finished, all these will be cleaned up from the stack. So the stack can be used and reused by all the function calls. And the order of this local variable, like here is a defined X and Y and above. The order of this local variable is defined by the hardware and also defined by the compiler. So the order is not fixed. It's not defined by which variable defined first, which variable defined later. So the order is totally depend on the system and the hardware. So that is what means here, how the calling stack is used. When a function call is made, the return address is put to the stack. The value of parameter are put on the stack. So this will be put first, then return address. Then the function save the stack frame pointer. This is for the operating system use. Then local variable will be put on the stack. So that's how the stacks work. So basically, the function's parameter, when a function call is executed by the CPU, this is how the stacks looks like. The function call's input parameter will be put here. Then the return address, basically where the CPU should fetch the next instruction. Then saved all the base pointer, then the local variables. In CPU, there are two special registers used by the operating system for this stack operation. The two special register is one is called a stack pointer, SP, stack pointer register. Another is a base point register, base frame pointer. So when this function call is just made, the base frame pointer register will be point to the starting of the local variable. So it will be point to the starting of the local variable. So this saved all the base pointers basically before this BP register changed the value, the old value will be saved here. Then the new value of the BP will be point to this location. And this is created as a linked list for all the functions on the stack. So operating system can easily find out where each function call, this part is saved on the stack. So that is used by the operating system. The stack pointer always point to the top of the stack. Basically, this is a place where you can push more data into the stack. So this is called the top of the stack. So that is a stack pointer. Right. So these are the two special registers in all the CPU. CPU has many special registers that the normal program code they cannot access, but they are used by the operating system. Okay. Any questions for this 2 pages of slides? Okay. We will refer back to this layout of the stack many times when we introduce the Stack Overflow. Then just a few words about Intel-based architecture. Because Stack Overflow originally is, because in old days, the Intel-based architecture is the dominant one. Of course, right now, Apple uses its own CPU and it has its own structure. The Stack Overflow for Apple's this M chip is could be different than here. And Intel-based architecture, like for all the register, for CPU has many register. There are many register. They are called a common register. This ABCD is a common register that can be used in whatever way you want. This SD can usually used by special instructions, like by multiplication instruction, by division instruction. So they are mainly used by those instructions. And this BP, SP, these are the two registers for base pointer and the stack pointer. So these are the special registers. Normally, you cannot access by your own code. They are used by the operating system. This IP is instruction register. This flag is for control flag register. These are all system registers that your own program code cannot access. This instruction pointer will always save where to fetch the next instruction. So that's the instruction pointer means. The flag is basically changed whenever you do any plus, minus, or comparison operation. Whenever you have a plus, minus, or compare operation, the result will change the flag. Then the flag can be checked by other instruction to see what's that result for your previous computation. And for 16-bit computer, it's called AX, BX, CX, DX. And for 8-bit computer, this is AL, A low, this is A high. And 32-bit computer is like this, it's called EAX. Intel-based computer using this way because they want to be able to backward compatible. So basically on 64-bit machine, you can still run 16-bit machine's code, but because 16-bit machine code, they only use AX, CX, DX, EX, BX in their assembly language, so that it just means those code can still run. It just it only use a fraction of the register. The most of the register they will be idle, but you can still run those very old code. Even you can run 8-bit code because in those instructions you use AL, and you can still use this 64-bit register for all those operations. So it is backward compatible for the Intel-based structure. Smashing the stack. So this is the original publication to publicly introduce the stack overflow attack. The general idea is to overflow a buffer such that it overrides the return address. When the function is done, when this full function is finished, the CPU will try to fetch the next instruction's address from this return address place. If you modify this carefully, CPU will fetch the instruction, will jump to whatever address on this return address place. And this new jump place where we can put the code in the buffer such that this new jump place will jump to this buffer part, then run our own code. So we put some code in the buffer and set the return address to point to it. So that's the basic idea for this so-called smashing the stack attack. That's a basic idea for buffer overflow attack. If we use graph to represent it, then it's like, suppose this is a full function. This is a subfunction in your program. And this function has this vulnerable code in it, has a local variable in it. Then when this full function is called, this is a stack layout. It will be the input parameter. The input parameter is S, so address of the S. Then it will be return address. Then it will be saved BP pointer. Then it will be local variable. For this full function, we only have one local variable, buff. So this is local variable. If attacker smash this stack, smash this full function, attacker can put a longer input such that it will overwrite the, it will, because this string copy will copy the input, right? The string copy will copy everything and overwrite both this save the BP and return address. You generate this input string such that you modify this return address place, make this to point back to beginning of this path, where in the beginning of this path, you put your small program. Usually it's just a shell, a small shell program. Because for any operating system, you can write a 20 bytes to 50 bytes code that can generate a shell. So that's as long as this path can hold that shell code, you can put shell code here. So when this full function is finished, CPU will fetch the new return address. CPU will fetch the instruction from here, then run this small code. So this will generate that shell for the remote user. So that is a basic illustration how this Stack Overflow could happen. Basically, overwrite a local variable such that you overwrite the return address. You carefully generate the value to overwrite return address such that this value will give the location of your program code in the beginning of this buff variable. And then your own program will be executed when this full function finished. Okay, any question for this illustration for the Stack Overflow attack? Okay, okay, I will try to finish the slides next class. Basically, what caused the buffer overflow attack? We introduced one function, this is a string copy. There are many other functions that can cause this buffer overflow attack. And some programming habit, bad program habit will also introduce such kind of unchecking copying of data from user input that can lead to this Stack Overflow attack. Okay, that's all for today's class, and see you next Tuesday.
Thank you.
Yeah, thank you. Okay, let's start. This is lecture 5 for the malware analysis class. I will finish the introduction of the Stack Overflow with some coding examples, then focus on using GDB. GDB is basically a general purpose debugger in Linux, and we can use GDB to find out the memory information for a running program. So that will prepare you to understand how you can do the Stack Overflow attack by yourself. So let me first finish. Okay, so the first programming assignment will be either released this Thursday or next Tuesday, depending on the teaching schedule. And I will create a submission tab for the proposal, term project proposal within this week. But as you know, the term project proposal is due just in a week before the spring break. Okay. Let me continue this. So last time we introduced the basic concept for Stack Overflow. Stack Overflow is a original form for the buffer overflow attack and the easiest one for buffer overflow attack. This attack, let me see what's the question. Which assignment is due next week? Next week, there's no assignment due. I will release the first programming assignment either this Thursday or next Tuesday, but it will be due about 10 days after I release the assignment. So it will not be due next week. Okay, for Stack Overflow is basically when you have a vulnerable function in your program, and the vulnerable function which has some vulnerable function call that doesn't check the boundary of the copying of user input to internal variable. Like internal variable is buff. This buff only have 100 bytes, but string copy doesn't check the user input string, how long it is. Then this copying, if an attacker supply a string s that is bigger than 100, then this is lower address, this is higher address. When you copy from lower address to go up. After 100 bytes, you will overflow some system parameters on the stack, like saved BP, return address. And if attacker make it very carefully, such that the attacker supplied input contain two components. One is this small program at the beginning of the input, which will fill in at the beginning of this local variable buff. Usually, this small program is just create a shell. On Linux machine, creating a shell only take 20 to 30 bytes, no more than 40 bytes. So it could be very small, tiny, and very efficient attacking code. And after that, attacker will modify at a specific place where it can overwrite the return address with the modified address. This modified address will basically point back to the starting of this small program. So basically, Stack Overflow is once you find the vulnerability, you create this user input, you create this attacking input. The input will have two components. One is a small program. Second component is you overwrite the return address at the correct location. You need to find out where the return address is. Then you modify that value, that address value, to be able to point back to your supplied small program. So then when this full function finished, CPU will try to fetch the address of the next instruction. Return address just means the address of the next instruction after full function. Then CPU will fetch the address from here and start to run this small program. So that's the Stack Overflow. The basic concept for Stack Overflow. And what caused the buffer overflow? The string copy is one example, but there are some other examples, like in traditional C programming language, there are many function calls that don't check the size of the user input, like this get command. Get is basically read user input line until user press enter. So you can think this traditionally, it's a command line input. And well, the created buffer can only have limited size. So no matter how you define this limited size, attacker can always input this line long enough to be bigger than this allocated size. Then this will create buffer overflow to this variable. So one general principle is that when you write a code by yourself, don't use the get command, but use this fget command. Because f means the file get. File get command where you can specify the size of the input. This fget standard out just means a get from the user's keyboard, standard input user keyboard. The size will specify how many bytes you are allowed to copy to this variable. So instead of using gets, you should always use fgets to give a limit on the copying size. String copy is also another one famous function. It doesn't check the size of the source. It directly copies the source string to the destination string. So instead of using string copy, you should use a string uncopy. And then you can specify, the third parameter will allow you to specify how many bytes you can copy in maximum to the destination. And the string copy also assume that this source is now terminated, because in C program language, a string array is treated as until it meets the first zero value byte. Zero value byte just means null byte. So if this source string doesn't have a zero value byte at the end, the string copy will copy byte by byte forever until it meets a memory value that is equal to 0. Then it will stop copying. Okay, any questions? Okay. And so for this example, very simple example, can you find out what's the vulnerability for this one? This uses a string uncat. So the programmer already know that we should use this n type of string functions. Like a string copy without a size limit. String uncopy, this n will specify how many bytes you allow to copy. So this already put in n specified size is the size of buff. So copy no more than the size of the buff to this destination. So the original, so the problem is here. So even though the programmer realized that he should use this n type of string operation, so never copying bigger than the destination buffer size by specify size of. However, this is a CAT. It's a concatenate operation. Concatenate operation means that whatever you copied will be added together to the original string in this destination. Originally, you already have this 1, 2, 3, 4, 5, 6, 7. You already have 7 bytes in this buff variable. So if you still allow 20 bytes to be copied in, because the size of buff is 20 bytes, so size of buff will become value 20. If you still allow copying up to 20 bytes, because of the concatenation, the destination buff will be able to copy up to 27 bytes. Then 27 bytes will overflow the created memory for the buff. So even if you use this n type of operation, you still, it's possible to make some mistake because of the logical reason. So when you use this n operation, don't just use size of. You should think about the logic. How many bytes are allowed to copy in? So here this is a number of character to copy, not the buffer size. So for this concatenate operation, you should not allow the number of buffer size to be copied in. Should only allow the number of remaining bytes allowed to copy in. So you can use the size of buff minus size of size of prefix. So that is the remaining character that you can allow to copy in. And this is this code problem that will cause a buffer overflow. Another common mistake is given size of path as the third parameter. Size of path means the size of the source. So remember the first is the destination, the second is the source. If you use size of source, then basically means that you do not specify the limit. So whatever size of the source, you allow it to copy in completely. Then that will remove the purpose of this N type of operation. So size of path will certainly be wrong. String copy. Well, string copy. This question is that do string uncat or string copy append the null character at the end of destination buffer? The answer is that string copy will copy the null byte from the source to the destination. So if the source has a null byte at the end, then the destination will also have the null byte. Because string copy will copy forever until it meets the null byte. So for string copy, the destination variable will always be null terminated. String uncat, then it's possible that the null byte will not be able to copy in because you specify how many bytes you copy. If the source string is much longer than that allowed limit, then you only copy that limit, that number of character to the destination. In that case, the destination will not have the null byte at the end. You can check the string and copy. You can see since that's not automatically null terminated if n is reached. So we need to manually add this null byte at the end. So if you use this string uncopy, the safe way is that right after you use string uncopy, you should manually assign a null byte at the destination string to make sure that it is null terminated. So this is Microsoft AI's recommendation. So spot this defect. This is a web server processing users' input URL. So source string, destination string. This base URL is this one. Then string uncopy will copy up to, because this source is a 9 size of bytes. So we only allow copy up to 9 bytes, so it will not overflow this source string. Then since the source string is no more than 9 bytes, so the next time we can use the string copy without checking this size of the source anymore. So that's the logic for this programmer to write this code. So the defect is what the student have just asked that I have answered. When you use a string uncopy, it's possible that the final 0 value byte is not copied to the destination. Remember, this is that destination string. This is source string. This source string actually is 10 bytes. Here is a non-character. But for ASCII array, string array, the size of the ASCII array is the number of character plus 1. The plus 1 means the 0 value byte at the end. So this string is actually 10 bytes. You copy only 9 bytes, so basically means that you only copy these characters. So this source SRC will not have 0 value byte at the end. Then when you do string copy, this one is not a 0 value at the end. So string copy will copy byte by byte until it meets 1 byte of memory that has 0 value. So you don't know how many bytes will actually be copied to the destination. It totally depends on what's the value on that memory at that moment. So this string copy will overflow the destination string. Because of this, this is not a 0 value terminated array. So this base URL is actually 10 character long. It's not just this 9 character, it's 10 character long. So the source won't be now terminated. So string copy will overrun the buffer destination, this destination variable. It copies byte by byte until meet value 0 bytes. So that's what caused this buffer overflow attack. What caused this buffer overflow vulnerability? We can say this is a buffer overflow vulnerability. Okay, so basically when you write program in C, when you do any string operation, you should always keep in mind of this now terminator byte for all the string operation. So don't forget about that when you do C programming. Of course, if you use some other programming language, I believe if you use Java, then the Java language will take care of this now byte by itself. So when you use Java to do coding, you don't need to worry about this now 0 value byte at the end anymore. So that will make these kind of easy bugs to go away. But of course, there are some other potential bugs that could create it even if you use Java programming. So don't just replace string copy by string uncopy. Instead, you should use this way: string uncopy, and specify that size of it's not that destination size should be destination size -1. Then you make sure that the destination string is ended with null byte. In this way, it will be always ended with null byte. Then all the other later on string operation you will not overflow the future operations. And this destination string will always be less than or equal to the original memory you allocated to it. So this one will make sure that destination will be always now terminated. Well, string copy is just one command. You don't use both one at the same time. You basically should always use string uncopy. Do not use string copy. It just means that whenever you use string uncopy, it's best that you add this instruction right after string uncopy to make it as a standard programming habit. So in this way, you can guarantee that it is terminated before at the boundary. So a strongly typed program language could, of course, enforce that string are always now terminated, just like Java will take care of this one by itself. But Java will deal with this memory allocation, dynamic memory allocation by itself. So in that sense, Java programming is much slower than C programming, because C programming is more low-leveled programming code, and the memory has been fixed, and all the operation will be much more efficient. It's not like Java will run much slower. So for that reason, many software, their interface may be programmed by Java code, but internally, their internal modules, most of them, they are programmed by C or C++, just this a little bit lower program language for efficiency purpose. Okay, find this code vulnerability. This is not but because of the string operation. It only has a memory allocation. So the basic idea is that we open an input file. We get the user input length, like a user input like 100. Then we create a buffer. We create a dynamic allocated memory that is 10 bytes larger than the user intended user wanted length. This plus 10 bytes is very common. Like whenever you do any coding, you should add some marginal leeway so that if something goes out of bound, you can still handle it. You will not create problem. So suppose this one is that you want to read a social security number in this input file, and this length is ask a user to tell the system how long is the social security number. Then we allocated just a little bit more than that to incorporate some abnormal social security number that is longer than the normal one. So then we can read the data from this input file. So that's the basic idea for this code. The idea here is that if user want 5 bytes, then we will allocate 15 bytes. So it will always be large enough to hold the input. The problem here is because it doesn't check if whether user input a negative value or positive value. So we assume that the user input basically specify that the user want to input 100 bytes or 200 bytes. But what if the user is attacker? He or she just input like -5. So if this is -5, then this length is -5. Then -5 plus 10 will become 5. So memory allocation will become 5 bytes. However, this read function, this length will be treated as size t. So all the memory type of operation, the integer usually is basically this is specify what's the maximum bytes I will allow to read in. It's just like this n in this string operation. And in all this string operation, this n, this is treated as a positive value and always treated as positive value. So if you input a negative value here, it will still be treated as a size t type. Size t type is unsigned int. So if this length is -5, it will still be treated as unsigned integer. The -5 in unsigned integer, it will become a very big value. Because in current architecture, minus integer basically use the most significant bit as a sign. So if the most significant bit is 0, then this integer value is positive. If the most significant bit is 1, then this integer value is negative. So that is how the CPU treat an integer variable. Basically, it uses the most significant bit as a sign. It doesn't treat that as a value anymore. So if this length is -5, then that means the most significant bit is 1. And then when this is treated as unsigned int, there is no sign anymore. So the integer value will become 1 something. And that will be a very large integer value. So this just means that we allow to read in tens of thousands of bytes into this buff variable, where the buff variable you only allocated 5 bytes. So doesn't check if the user input is negative or not. Then this buff will only have 5 bytes, and the length -5 will be casted to unsigned int. The unsigned int -5 will be a very big value for an integer. And this will means that we will allow to read in tens of thousands of bytes to the destination buff. So this will overflow this buff variable. In this case, it will be heap overflow because this buff variable is a dynamic allocated memory. So it doesn't exist on the stack. It exists in the heap section in the computer memory. So this is one implicit integer casting bugs in C language. It's very hard to spot because in many cases, we don't really know whether the definition of an integer in a function call is signed int or unsigned int. This is unsigned int. But for some function call, they use signed int. And if you give those unsigned int with a negative value, then it will be implicitly cast to the unsigned. And C compiler, well, this is not true anymore. Right now, if you do compiling of this code, C compiler will actually give you a warning to saying that this length variable you define as int, this is a signed int, where this read function need to use unsigned int. So compiler will give you a warning saying that there is implicit cast in this input to the read function. So compiler will give you this warning. It's just many programmers, they just ignore those compilers warning message because if your program is large, your compiler will give you a very, very long warning list. So most programmers, they just ignore them. And this implicit cut, it's because of this integer has size. And for signed int and unsigned int, they have different size. It is machine dependent. For example, on Eustace machine, probably on most machine is still the same. The character, when you define an integer as character, then this integer will only use 1 byte of memory. And character is treated as a signed integer. So a character a variable could be negative, could be -10, -20. So character value will become -127 to positive 120. You should not assign a value bigger than 128 to a character value. So unsigned character, you can use all the 8 bytes for the value. So the value is between 0 to 255. Signed character means that you can only use 7 bits for the value. The most significant bit in the beginning is a sign. So you only have 7 bits for the value. So that's why unsigned character, let me see, what's the, So unsigned character range is 0 to 55, and signed character is minus 128 to positive 127, because it can only use 7 bits for the value. So that is how the value is determined for a signed character. So if you do an implicit cut from a signed character to an unsigned character, the value will be changed to what? Let me see if ChatGPT can give me. So minus 10 in a signed character, when you do implicit cut, it will be treated as 246 as an unsigned character value. So if you define a character value where later on in the function call, the function input parameter should be unsigned int or unsigned character, then that value minus 10 will be treated as 246. So you can see that the value has been changed. So whenever you use integer, if there is a casting between the unsigned and signed, then the value will be changed. The value could be very different. So that's the underlying problem for this integer overflow bugs. So a short variable, short integer is 2 bytes. Basically, you use 2 bytes to save a short integer variable. And signed short is minus 32768 to positive 767. Unsigned short, you can use all the 16 bits for the value. The biggest value is 65535. So that is unsigned short. Int usually is 4 bytes, so of course it's longer. Long usually is 64 bits. It's 8 bytes. There could also be a casting if you define a real number, like if you define a float, where if it's a float, even for float, there is a limit, even though it's not integer, but still it has a limit. If you implicit cast, then it will have its own problem. So we can try this by yourself to see how the value has been changed. Like I have provided this overflow code. You can upload it to use this, and basically it has all the code, all the example code shown in the slides. This is let me make it bigger. Okay, so for example, for this example, we define the short variable is 32767, which is the upper bound for the signed short variable. Unsigned short variable, the upper bound is 65535. Here I just print out the original value for x and y. Then I do this simple addition. We just add 5 to each variable, and you print out the value. If there is no this overflow problem, then this x plus 5 should be 32772, right? So that should be the value. But because this limited size of the short variable, this will overflow that 15 bits value part. Then overflow will cause this to go back. Whenever you do overflow, you will actually go back from the biggest value to the smallest value, then you go up. So that's how the overflow will happen. And you can see what is that. In C code, a simple compiling is that just use GCC -o integer. So -o is means the output executable code. We still call it integer. This is input C code, and you run integer, and you can see that when this one added with 5, and it will go to the lower bound. Lower bound is 32768, and the added another 4 value will basically move up 4 value. So this x value will become -32764. So you can see this one has been overflowed. For this y value, if you added 5, it becomes 4. Because when you add 1, it will overflow to go back to the starting point. Starting point is 0. Then you add the remaining 4. So the value will become 4. So whenever you do integer operation, you should always keep in mind whether it could cause the integer to overflow or underflow. Overflow means when you do plus operation. When you do minus operation, it's possible you can underflow your integer. So whenever there is overflow or underflow happened, the math operation output will be different from what you thought. And this is the inherent problem for integer, because no matter how you do it, your integer value will always have a limited size. You always could possibly have overflow or underflow problem whenever you have a mathematical operation on the integer. And in a program, in any program, you will always have many integer operations. So this integer overflow could happen in many places. And so it's very hard bugs that to detect and discover. This one is a similar problem as the integer overflow. This is reading. This percentage U means unsigned value, because the length is defined as size t. Size t is unsigned int. So this is the reading an integer value as unsigned value. Then we add 5. We read the buffer. Whenever you do this math operation, it's still possible that you could overflow this one. This is just to make sure that after you read in input, you make it now terminated. So what if if the user input length is close to the upper bound, just like the code here? This is unsigned short. So if the user input is close to the upper bound of that of the unsigned int, then this +5 could become a very small value, like a value 4, value 3, value 2, value 1. Then this memory allocator, you only allocate a single number of digit bytes to the buff. Where this read, you could read in more than 60,000 of bytes to the buff. So length +5 could overflow and become a very small value. So that's that is this integer overflow problem. The unsigned int, the value is between 0 to 4 billion. This is basically this is the size of the IP version 4 IP space. IP version 4 using 4 bytes as the IP address. So the range of IP address is basically as a little bit more than 4 billion IP address. So summary of the integer overflow is that there are two major issues with integer encoding. One is the implicit signed to unsigned cast. This one, there is no mathematical operation. It's just the type of the integer has been implicitly changed, either from signed to unsigned or from unsigned to signed. Whenever there is an implicit cast, the value of the integer could be changed unexpectedly. So that is one issue for the integer. Another issue of the integer is because of the mathematical computation. Whenever you have integer mathematical computation, then later on you use that integer value as the index of an array, either as the size of the array or as the index of referring for one entry in that array. Then this overflow or underflow could drastically change the value that you want it to be. This can happen for both signed or unsigned integer. Because both signed or unsigned integer, they have a range, lower range and upper range. And you could always have overflow or underflow issues for integer. So in many cases, integer overflow bugs is the starting point of buffer overflow bugs. So many buffer overflow bugs is not caused because of this non-automated byte. It's not caused by string copy, those string operation. It's caused purely by the integer, because whenever you do string operation, you need some integer to specify the index, the size. Then if the index and size value has been changed unexpectedly, then you could have buffer overflow bugs. This one defines the user input string, and it defined this buffer to be 256 bytes. And here it uses string length to check user input string size. If the user input string size is smaller than this maximum allowed size, then we will allow this string copy. This is smaller because after string copy, I can always define the last byte of the buff to be 0 value byte. So because this user input string is less than maximum buff, so this string copy will not overflow this buff variable. So that's the logic of this coding. The problem is that for any integer, you have a limit, size limit. Like this length is a short integer. Short integer, the upper limit is 36,500 something. So that is an upper limit of the size. However, if the user input is bigger than this 32,000, like 33,000 or 34,000, string length will return a value as 34,000, for example. Then 34,000, when you assign it to this variable, it will overflow this variable, because this variable, the upper limit is 32,000. Then this overflow will change the value. This is a signed int. So if you assign 34,000 to this assigned int, this value will become negative 1,000 to 2,000. So that's if the user input is longer than 32,000, the length will become a negative value. For example, if the user input is 34,000, the length will become 1,500 something. The length will become minus 1,500. Then minus value will, of course, smaller than 256. Then this string copier will be allowed to go through, where the input is 34,000 bytes. So this will overflow, definitely overflow this buff variable. So here is not because of the implicit cost reason. It's because of this size limit reason. It's not because of mathematical operation. Here we don't have mathematical computation on the integer, but this assign will overflow the limit, so that will cause the buffer overflow. Let me see if my code has this example. It's defect 5. Let me see. Defect 4. Defect 5. Okay, here I define this number to be like a 33,000. And this bad code is the user input and assign this size to the length. So if the input is 33,000, the length will become a negative value. So I first print out what's the value of the length. It then makes a string copy of the input. And this code is this part of code is basically assign just fill in character A to this string, and this string will be used as the input to the bad code. Right now, I define this string as 33,000 bytes. So this is a string array because at the end the string is now terminated. Then I feed in this 33,000 bytes input string to the bad code to see what will happen to this bad code. Defect 5. In Unix, / just means current directory. Just to specify, tell OS to find the program under the current directory. You can see that the value of the length after this string length operation, the value of length will become negative 32,000. Well, so it's not a negative 1,000 something. It's a negative 32,000 something, because it will go back from beginning and goes up. So of course, this length will be smaller than this 256 bytes. So this string copy will go through. Then string copy, it will be aborted by the operating system, because operating system has a defense mechanism that will prevent a user code to overflow the return address. So this is a stack smashing detected. Stack smashing detected is just above a stack overflow has been detected, and this running program will be terminated by the OS, so it will not cause the system to crash. And of course, if you change this code, if we make it not overflow, 30,000. Then this one will finish normally because here the length is 2999, and this condition will not go through, so the string copy will not be operated. So this will achieve its original purpose to make sure that user input length is smaller than this buffer size. So that will achieve the original purpose. If you don't have any integer overflow problem, then this code will be safe. So in Unix, if you do in the use case machine, if you do any editing by yourself directly, you can use this pickle command to do editing. And the pickle command is just because this is a terminal shell, so it only supports keyboard operation. After you modify, you do this Control X. This means Control X to exit, and Control X exit. It will ask you to save the modified buffer. You type Y to save it. File name, I just use the original file name, so it will change original C file. After that, you can do recompiling. You can use upper arrow to go back to your command history. So you don't need to type in that command anymore. You just use upper arrow to find the previous command you have typed, then run that command again. So this is how you use a Unix machine within this SSH shell. Okay, any question for this example code? Of course, if you are more familiar with this, doing editing by your own computer, you can simply download. You can simply like drag and drop. You can simply drag and drop this C code to your host machine, to your own desktop or laptop, then use your own computer's compiler, the editing software to edit it. After you edit it, you can drag and drop to the use machine, then compile on the use machine to run it. Okay. This is another box. It's not about integer overflow. It's just a string operation. This is a server processing user input URL. It first check if the URL is valid, satisfy the URL's format requirement. If it's not valid, you return. Then it check the user input URL, the length. If it's bigger than the maximum allowed size, because your buff is only maximum size. Here is the maximum size -1, because you need to reserve the last bytes for the zero value now terminated byte. So here is the use -1 here. After you verify that user input is smaller than the maximum size, we do this copying. Here, the programmer do the copying using this way, using this simple while loop. If the URL is not equal to space, basically if the URL is character string, it doesn't have any space, it will read in 1 byte and copy into this output, copying to this buff1 variable. So this out pointer is equal to buff1. So it will do this byte by byte copying until you meet the first slash. So the purpose is try to reading the domain name for URL. The first part for the URL is the domain name, web server's domain name. After the first slash will be the directory name for that. So it will first reading this domain name. Then after that, you copying the buff1 to the buff2. Because these two buff, they are same size. They are, this one is also now terminated. Well, it's that is the problem here. This while loop, it copy until this one. It doesn't make this buff1 to be now terminated, even though we specify copy maximum -1, so it will reserve the space, but it doesn't have a statement to assign the last byte in the buff1 to be now terminated. Then when you do string copy, this one may not be now terminated. And so it will overflow this buff2 variable. Another problem is that this while loop, so it will finish the copying until you meet the first slash. So for normal URL, you should have a first slash after domain name. But what if there is no slash in the URL? The user deliberately input a domain name that is very, very long without a slash. This loop will copying forever, because this loop doesn't check how many bytes has already been copied in. And this is an actual code in actual software. So this bugs has been exploited by the blast worm. So this bugs exist in Microsoft IIS web server. So that is in 2004, 2005. This Microsoft IIS web server has this script, has this coding in it. So it has been exploited by this blast worm and compromised several millions of Windows computers at that time. Okay, so that is integer overflow. We finished integer overflow. Here is another category of bugs. It's called format string bugs. Format string bugs is because of printf and scanf function. Printf is print out some output. And for many programmers, when they print out a string, the normal way you should use a printf quotation of s, then the variable name. And if you print out a string, you can simply just don't put that format that format string in the beginning. You can directly put the string variable in the printf function, and it will print out that string, that text message correctly without any problem. So many programmers just save the time of the typing. They directly put the string variable in the printf to print out the message, and it will not have any problem. However, if this printout message can be affected, can be modified by a user, the malicious user could modify this printout message in a way that will cause these bugs. So this program is vulnerable to format string attack, where calling program with string contain special character result in a buffer overflow attack. The problem is because if you don't supply this format string in the printf function, then the C programming will treat the special character in this string as the format string. So if this string has this special character, then C programming will treat them as a format string. and print out a later on message using that format string. Why this could happen? Because of this is actually there is a legitimate use for this. For example, if you want to generate some user formatted text, like if the user want to generate printout text in the format he or she want, then user can supply this format string by themselves. Then the printout message will satisfy that format. So it gives the users control on how they can make this output to follow certain format they want. So it gives the users more choice. However, this kind of freedom given to the user could also abused by attacker. Like some special format string, like a %x, will read and print 4 bytes from the stack. So this will cause a problem where attacker can use this format string to find out what's the value on the stack. They can use many %x in the format string so that they can print out 4 bytes, 4 bytes, 4 bytes, print out all entire stack memories content on the output. So they can figure out the computer's memories in content using this format string attack. They don't need any privilege. They don't need to log in to the remote server. They just use this supplied this format string to print out memory content. Then they can read some secret data from this server's stack. This %n will write the number of characters printed out so far onto the stack. So this enables an attacker to write a specific value onto the stack. So it will be able for them to change some value on the stack. For example, change some control variable, change some important values. So this C format string breaks the principle that don't mix data and code principle. If you mix data and code together, then attacker can supply some code in the provided data and modify your coding behavior. It's easy to spot and fix. So you can use a static analysis tools to analyze the source code. Whenever you see a printf function where it doesn't specifically supply a format string, then you give a warning and you can automatically change it. Like whenever you see this, you replace it with this command by explicitly provide this format string in it. When you provide the format string, then everything in this variable will be treated as data. So it will not be treated as code anymore. When you use this, the first some character will be treated as format string. So that's the reason behind it. Okay, let's see what's the problem for this format string vulnerability. Suppose for this a very simple code, if we print out argv1, well, in C language, in main function, if you use this input, then argc just is the number of input in the command line. So normally argc, if argc equal to 1, that means you put the execution program without any supplied option. If you supply multiple options, then this number will tell you how many different options you put in that command line. argv will save the command line's input string. So argv1 is the first command line's string, supplied string. argv0 is the execution program name itself. So this is the argv0. The second string in the command line will be treated as argv1. The third string will be treated as argv2. So that is how you can check the user supplied input. And so here, this printf, it doesn't have a format string. So the user is possible to supply the format string in this argv1. This is how the user can do that. Let me show this example. This is format. Okay, so this is simple code. Here, you just directly print out, here it's print out how many command options by argc. This is the first string. So if we this compiler will give you a warning that there is a possible format string vulnerability. So the compiler will actually give you a warning that here there may be some problem. And if we directly run this program, argc is equal to 1. If we run it here, argc is 4 because this is the first string. This is the second string. This is the third string. This is the fourth string. So argc is equal to 4. So this in the command line, the space is a separator to tell that the previous string and next string. And this argv1 is the first option after the program name, and the first option will print out. So normally, if you provide this string, if you provide this text, normally, then this printf will work without any problem. So that's why many programmers, they don't put format string in those text message printout, because it's just a waste of coding. You can achieve this function without any problem, print out the text message without any problem. The problem is that if attacker put a lot of format string at beginning, then attacker will be able to print out the value in the stack. So these are, every value is a 4-byte value. It is printed out as a hexadecimal format value. So this is the value on the stack. And attacker can use a lot of %x to print out the entire stack content. So that's the problem for this %x format string vulnerability. And this is another example. It's similar. It's just for the full function. In the full function, you put user input as argv1, and argv1 will be print out by this printf directly. So this one has this format string vulnerabilities, and it will print out the stack memory content. Originally, it will print out 11, 12, 13, 14 value. But I believe it's because of this defense mechanism putting the Unix. This one doesn't print out that value. Let me see it. So this is that example. If we of course, it will give you a warning, and And you can see these are the value printout. The value is not corresponding to this 11, 12, 13, 14 is because of this alignment of the variable is not aligned correctly. So it doesn't print out because it's every 4-byte value show up. So this printout 4-byte may be 2-byte into A3 variable, 2-byte into A2 variable. So the final value here is different. But once you put them together, you can still figure out that these 4 variables name value from this memory. Is there a way to? Okay, maybe I will find out whether I have a way to print out this local variable directly without these arbitrary values show up. Let me see. The value has changed every time value has changed because of this address randomization techniques used by Linux machine. I will explain them in next class. Okay, just a few slides left, and I will finish them next class. And so next class, I will mainly focus on this Stack Overflow using GDB. So explain how you can use this debugger to find out the stack memory location and return address where they are saved. So that's the precondition for you to generate crafted user input to override the return address correctly in order to generate the Stack Overflow exploit. Okay, that's all for today's class. See you next Thursday.
Thank you.
Thank you. Yeah. Okay, let's start. This is lecture 6 for the malware analysis class. And from the schedule, I will release the first programming assignment next Tuesday. So next Tuesday, I will explain a little bit more on the assignment requirement. But this class, I will mainly give this example analyzing the stack memory layout using GDB. So this is basic technique you will use for the programming assignment 1. So this class is very important to understand how you can do the analysis by yourself. I just have a few slides left for the introduction. And last time we mentioned the format string attack. The main format string attack is this %x and %n. %x we have demonstrated that it basically can print out the stack memory information. So if attacker want to attack a remote server, one thing is that they probably need to know what's the stack memory layout, what's the content on the stack. And then if the server program has this format string vulnerability, then attacker can use format string attack using %x to print out the stack memory information. Another control for the format string attack that attacker can use is %n. %n can write the number of characters printed so far onto the stack. So this means that if you want to write to the stack memory in that place with value, for example, value 100, then you can let your client program you can let the server program to print out 100 character, arbitrary 100 character. Then you supply with this %n in the format string attack. Then this 100 will be written to the stack on the current position. So this is a way for attacker to modify stack memory content on a remote server. So these are percentage n. So percentage x, we have demonstrated last time that you can print out the stack memory information, one value for every 4 byte. Percentage s is just a normal print an ASCII string. So percentage s will print next stack memory word as the memory. So here, if you use printf, use percentage s, you should give a variable, right? The variable is a string array. Then printf will print out that variable until it meets the first null terminator byte. But if you give this to printf, there's no variable after this control string. Then this printf will treat next stack memory word as the memory address and print everything until first value 0. And so basically printf will use the next memory place to fetch the string from that location and print every byte until it meets a null byte. So this one will certainly could cause overflow of the current stack and cause a segmentation fault. But before it caused segmentation fault, it could print out many other things. So at least this one could cause your program, the server program, to crash. So percentage n is write 4 bytes, percentage hn write 2 bytes at once. So enable attackers to mount code injection. So they can introduce code into victim memory using these format string bugs. One example this percentage n can be used is that this simple example. So suppose you first use percentage s to print out user supplied string. For example, this user supplied string is hello. Then after that, this percentage n will basically print out how many bytes you have already printed out before. So since we print out argv1, that is 5 character, then this percentage n will write 5 value to the variable here. Therefore, this variable value will become 5. So you can see this, this one is not a format string attack. This one just demonstrates what does this percentage n does. It just print out the value that how many bytes you have printed out before. So that's the function for this percentage n. Another related attack to buffer overflow is this function pointer override. Stack overflow is we overflow the return address in the stack, but people have presented effective way to defend against the overflow of the stack address. But if you do overflow of some local variable, suppose in your function you have a buffer, a string array buffer variable, you also have a function pointer variable. Function pointer variable, it just means that sometimes when you generate a program, you want to give the user some more control. Like suppose you generate program is a calculator, and you provide this plus, minus, multiplication, division function. And you want the end user to be able to select which function, which one of these 4 mathematical functions the user want to use. Then your calculator program can write that user input function as a function pointer. Then this function pointer will have 4 possible values. So each function, each possible address will point to one of these 4 mathematical computation subfunction. So that is usage for function pointer. So for more advanced program, they have a lot of function pointer in it, give the user more choice. So if you don't have this function pointer way in the program, then your calculator need to put this 4 mathematical operation in 4 buttons. So user have to click a plus button, minus button, or this, and so the program control. But if you provide function pointer, then user doesn't need to do all those operations. So function pointer has been used widely in commercial software. Then function pointer is just a pointer variable, and it is a local variable in this subfunction. So it could be a neighborhood of this buffer variable. So if you overflow the buffer variable, and if this one is in the higher address of the neighborhood of buff, then you will be able to override this function pointer as well. So attacker can just override function pointer. Remember, function pointer is like the return address. It will tell CPU where you should fetch the next instruction. So attacker can change this to be their shellcode address. Then when this function pointer is executed, the CPU will run the attacker supply shellcode. So in the same way as the Stack Overflow attack, change the control flow of the CPU. And this function pointer overwriting is much more difficult to defend because function pointer is just a local variable. It's not a system. It's not a system memory. Like return address is a system memory. Your program should not is supposed not to touch it. So the operating system has a way to verify and protect it. But for function pointer, no operating system can protect it without any special checking on all the local variable. So function pointer overwriting is much harder to defend than the return address. And so when there is a commercial software coming out, how does attacker find out any bugs in a software? Attacker can find buffer overflow by run the target server program on their own machine. So when the software is out, they can run it on their own machine, then issue all kinds of requests to the server program, and try to issue all the user supplied to input to be as long as possible with a special character in it. If the server, well, it's not a web server. If the server program is if the software, commercial software crashed, then you search for the core dump, because for any operating system, when a program crashes, operating system will save the memory layout onto hard drive as a core dump. Then attacker can search the core dump to find this user supplied special character. So this one is try to locate where this crash happened in the target software, because target software could be very long. So you first need to identify if this crash happened, where it happened. So you use this way to do that. There are many automatic tools that can help you to detect, to analyze this. Here is just some example. But again, this need some advanced techniques for the attacker, because they need to first be able to do this automatically. Second, they need to analyze this core dump, which need some reverse engineering and debugging techniques.